In this video, I'm going to introduce you to the idea of a protecting group and what happens when you have a functional group or two functional groups in which you want to do chemistry on one functional group and you don't want to do chemistry on the other one. So one thing that chemists often do is we can protect one functional group, do chemistry on the other, and then deprotect it. And we're going to see this throughout this video. So oftentimes acetals are used to protect carbonyls as that functional group. Um, Here we have an example where I have a ketone and I have an alkyl halide on the same molecule. And I want to do chemistry on the alkyl halide, and I don't want to do chemistry on the carbonyl. So what if I wanted to undergo a substitution reaction and convert the alkyl halide into a nitrile? I run into a problem because cyanide actually can react with both the alkyl halide and the carbonyl we've seen um, uh, in previous videos. So what do? Well, we're going to take and we're going to protect the carbonyl and make it into an acetal. And so we can react it with an alcohol, an excess amount, and basically we can simply um, dissolve this in an alcohol if we wanted to and add a little acid catalyst, or we could actually add a particular alcohol with an acid catalyst. And we'll see it both ways. And of course, when we do that, we form our diether or acetal. And the important thing about acetals, or these diethers, is they are stable in basic conditions. They're not stable in acidic conditions, so this is something we have to worry about, right? The acid-base conditions that we're in, but they're definitely stable in basic conditions, which if I'm doing a nucleophilic substitution reaction of an alkyl halide, that is going to be in basic conditions. And so I can then take and I can react it with sodium cyanide. The cyanide isn't going to react with the acetal, right, the diether linkage, so I don't have to worry about that, and it'll simply undergo a substitution reaction with the alkyl bromide. And so now I still have my acetal, but as we've seen, acetals are reversible in acidic conditions. So if I simply add water with some type of acid source, then I can regenerate my carbonyl. And that is how we can synthesize this particular compound. So let's say I wanted to make cyclohexanone from cyclohexenone. And if I think about, how I would go about designing this particular synthesis, I would say, okay, well, I have an alkene and I want to convert it to an alkane. How do I do that? Hydrogenation. The problem is that hydrogenation reduces pretty much all double bonds. So they'll reduce the double bond of an alkene. They'll also reduce the double bond of a carbonyl. So how do I work around that? Again, I can protect the carbonyl and then do chemistry on the alkene. And so what do? I take and I react cyclohexenone with ethylene glycol in the presence of para-toluene sulfonic acid, right? So para-toluene sulfonic acid is my acid source. Ethylene glycol is a nice diol, and when I react it together, it forms a cyclic acetal, which is very stable. It's stable in basic conditions. It's stable under hydrogenation conditions. And so I can simply take this, react it with hydrogen over platinum, reduce the alkene double bond, and then I can regenerate my carbonyl, right? So this is something that you're going to have to think about from now on. when you have two or more different functional groups and you want to do chemistry on one, is it going to affect any of the other functional groups that are present? And is there a way to protect it? So one of the other things that acetals can do is they can protect alcohols. And if you think about it, the way that we make acetals is from carbonyls and from alcohols. So since acetals involve alcohols, we can also protect alcohols as well. And a very common reagent to protect alcohols is what's called dihydropyran. Dihydropyran. And it creates a tetrahydropyranyl ether when it reacts with an alcohol. And we call these THP ethers. So what does this look like? Well, you have an alcohol and you have dihydropyran, or DHP for short. So dihydropyran is an ether with an alkene on it, right? And in acidic conditions, what's going to happen is you can, we'll go through the mechanism of this, but you can produce, this is called a THP ether. A THP ether. And so you see, if you look closely, we have a carbon that has two ether linkages off of it, and so we have an acetal. So let's see how this works. We know that in acidic conditions, alcohols are going to protonate, so you get the alkoxide ion, right? And so this alkoxide ion can then react with DHP. And what happens is the oxygen donates a pair of electrons toward the alkene, making the alkene more nucleophilic. And so that alkene can then remove a proton and essentially get protonated by the alkoxide, the alkyl oxonium ion. And you end up with neutral alcohol plus now a protonated DHP. And now that alcohol can react at the carbon. And so, if you think about this structure, it almost resembles a protonated carbonyl compound. So the alcohol attacks, and the carbon-oxygen bond breaks and goes toward the oxygen. We end up with this structure right here. And so now you can see if I simply deprotonate this, then I will generate my THP. So I can deprotonate it with alcohol, because we have an abundance of alcohol present. And so deprotonation occurs, and the result is THP ether. And so this is a great way of protecting alcohols because, again, it can be reversed. These reactions, acetal reactions, are reversible in aqueous acidic conditions. So if I need to regenerate the alcohol, I can do so simply by adding water in acidic conditions. Let's look at an example. Say I have a structure where I have an alcohol and an alkyl halide. And let's say I wanted to do a Grignard reaction, right? I have an alkyl halide. I know I can convert the alkyl halide into a Grignard. So I react with magnesium and I get my alkyl magnesium bromide, and then I can treat this with some type of aldehyde or ketone, and followed by an aqueous workup, and generate a new alcohol, right? This is what we talked about in previous sections in this chapter. So, easy to do, right? Well, there's a big problem. And that big problem is that Grignards react with alcohols. They react with water. They also react with alcohols. And so they'll deprotonate an alcohol, and you lose the Grignard. So instead of having a Grignard there, it simply will add a proton and you get an alkane. So how do you work around this? Well, you can protect the alcohol. And if I take my compound and I treat it with DHP in the presence of an acid, so para-toluene sulfonic acid, then I generate my THP ether. And so again, notice the acetal there, and now the ethers are unreactive in basic conditions. I can then react my alkyl halide with magnesium, generate the Grignard, and now I can react the Grignard with whatever aldehyde I want to, followed by an aqueous acidic workup. And in that aqueous acidic workup, I can regenerate the alcohol, so the THP ether will revert back to the alcohol, right? And so that's how we would do something like that, protecting the alcohol functional group. Now you can also use silyl ethers to protect alcohols, right? So you can use make THP ethers, or you can make silyl ethers. And a silyl ether is formed by taking alcohol and reacting it with a silyl chloride. So here we have some trialkyl silyl chloride that reacts with that alcohol, and it's a simple substitution reaction. And I form a silyl ether. This is a silyl ether. And of course I generate HCl in the process. So if we go back to that previous example where I have an alcohol and an alkyl halide functional group, right? So I could protect that alcohol reacting it with trimethylsilyl chloride in the presence of dichloromethane, and I form my trimethylsilyl ether functional group, right? So I functionalized the alcohol, I've protected the alcohol, and so now I can again treat this with magnesium to make my Grignard, and so on and so forth, right? And the cool thing about this reaction is that the way that you deprotect is using ammonium fluoride. So it's very mild conditions, and ammonium fluoride's cheap. It's soluble in alcohols. It's soluble in water, and so I simply take my protected my silyl ether, treat it with ammonium fluoride, and I regenerate the alcohol plus trimethylsilyl fluoride plus ammonia. Now the driving force for this reaction is that I'm forming a very strong silicon-fluorine bond, and that in essence drives the deprotection and formation of my alcohol.